This talk is probably going to be pretty lightweight, considering the kind of talks that we've been having at LambdaConf all this while. So I'll probably breeze through most of the material fairly quickly. Feel free to give me a shout, and we can go back and look at code and things if you so desire. So it's a very easygoing talk, right? My name is John Azariah. I work for Microsoft Research in Redmond. I actually get to do FP with F# in my day job, so I'm a pretty privileged kind of guy. But obviously, my background isn't FP. Most of us, just like most of us, been doing C, C++, C#, /Java, whatever, and then sort of applying functional programming concepts to the way in which we do things. Before I joined Microsoft, I was a consultant. I wrote boring line of business applications, if that term means anything to you. And obviously, when we do that kind of thing, you spend a good amount of time trying to model your domain properly, and you have multiple ways of doing that, and there's books and formal mechanisms for doing it, so on and so forth. One thing that didn't become apparent until I started using FP was the use of types as a modeling scheme. So you can model your domain using algebraic data types. And this is kind of alien to a lot of people because the concept of the algebraic data type hasn't actually leaked out sufficiently into the C# and let's say the Java world. So, who's done modeling of a business application starting with the database? I mean, that used to be the old-fashioned way of doing it. So you land up trying to figure out, third normal form or whatever the heck it is, and then try and work things out from there. And so you got business rules that are encoded in some document that has to be sort of human interpreted and human explained and then human re-explained, and then somewhere along the line people forgot what the actual business logic was supposed to be. And it becomes very difficult to actually start with that approach. Then they came up with the idea of a model first kind of approach, which is also kind of interesting. But at the end of the day, really the problem is that on the database side, we think of the structures as actual values. A record with my ID and my social security ID and my name and so on and so forth is one entity. But the ORM that's interacting with the database can have multiple objects with multiple references talking to the thing, and each of them has their own sort of view of the world. And virtually every ORM problem that you have stems from the fact that you have to synchronize those two things to some degree. And so getting down to using value semantics and working with things from a sort of event-driven or a immutability kind of approach, these are some of the new concepts as far as the traditional programming world is concerned that they're starting to encounter now. But from an FP perspective, we've actually known about this for some time. We've had type composition where you can consider a tuple of types as a product of the individual constituent types. As it turns out that the cardinality space of the tuple is exactly the product of the cardinalities of the constituent types. And we kind of used to that. Some types are a little bit strange to encounter because, in effect, they represent a cardinality that is the sum of the constituent cardinalities. And that's an effective way of representing choice in your domain design. And it makes it much easier to actually constrain your program domain so that you don't have to deal with the possibility that something that looks like a valid record isn't really a valid record in the domain. You can actually encapsulate a lot more strictness into the design of the domain by using these sum types. And the combination of immutability, value semantics, the idea that an object, that something is a value and is not just a copy or a reference to something, means that you can talk meaningfully about a problem space. So if you think about just a point object, you can have a million point objects, all distinct from each other just because they have different references, all talking about exactly the same point in space. And in some sense, that's wasteful and obfuscating. Whereas it'd be much cleaner if you could talk about a point as being a value, and when you have that, you can actually reason better about what kind of problem you're trying to solve. So record types, people have been using record types in some regard for most of these languages. I mean, they tend not to be mutable, but your typical class or a structure or whatever it is in effect a record type. So if you have a structure, for example, that is got a string and an int, then and you have 10 million strings possible and 4 billion integers possible, then your structure will have 10 million times the 4 billion product space that you can work with. And so we're quite used to working with that. As it turns out, C#7 just came out a few weeks ago and introduced mutable record types into the language. So this talk is based on a library that I started working on some time ago, has an implementation that isn't going to jive with that. So I'm going to skip the record types for the moment, and we're going to talk about sum types for the rest of this talk, if that's okay with you guys. Right. Sure. The question was, if you're not going to move to C#7 in the near future, will it still be useful to talk about this? The answer is absolutely yes. But what we'll do is we'll work through the sum types, because first of all, that is actually a little more esoteric in terms of a concept to a typical C# programmer. Then we'll dive through the process of actually developing a sum type, and then we can come back and look at how that same process would apply to building a record type. And you'll find that it's actually a lot easier to do this. So I'll still move on with the sum type, just to get moving. So in F#, you can define a sum type, the quintessential one being the maybe sum type or the option sum type, which represents the presence or the absence of a given value. And so in F# you would just write those 3 lines. Takes a bit of a whack to the head to get the syntax right, but the moment you get that, it's pretty clear. Yes?
I apologize for is a sum type, you said SUM?
Yes.
Sum type, and that's the same as an ADT?
So, okay, I should have been a little bit more precise at the beginning of the conversation. The reason they're called algebraic data types is a brilliant question, by the way, and thank you for raising it, because I actually skipped over that totally. The reason they're called algebraic data types is because you are now performing algebras on other types. So you're building bigger types based on smaller types. And there are 2 ways of doing this. The traditional way of doing it is to create a record where you have several members of the smaller type constituent inside the bigger record. And if you think about the cardinality of the values in the record, it's going to be the product of the cardinalities of the individual constituent types. The other side of that algebra is the sum type, where you construct a type from other types where the cardinalities add up, not multiply. And if you think about what that means, what you're really saying is the value space of the sum type, in some sense, represents a choice between the value states of the individual constituent types. So they're variously described as choice types or union types or sum types. And that's why it's called algebraic data types. The algebra is on the type, not on the stuff inside. That's right. There are two different sides to the type algebra that involve addition and product. Yeah, there are some esoteric ones. We can run into one or two of them later in the talk. I'll actually show you how you can actually build one. But for the purposes of actual reasoning about things, the algebra of multiplication and the algebra of addition turn out to be pretty powerful, and they cover almost all the useful cases. There are things like quotient types and difference types, and I'll show you how we can encode one of those in here. But in any case, pay attention to this, because this represents when something is a maybe of type T, it really says it's either nothing or it's a sum, it's a none or a sum of that value, right? So it represents the presence of the value and its value, and the absence of the thing as a choice. So just by using this specific union type, it's possible to walk away from a large number of null pointer exceptions. Because if you think about what a null pointer exception is, when you have a value, what they think is a value, but really is a reference, they're saying that they conflate the two things together. It's either something that points to something or nothing at all. And it's up to you to figure out what it is. Whereas here, the difference is actually encoded in the type itself. So you can actually model the absence of something very effectively using this specific union type. So I'll use this union type all the way through, simply because it's one of the first ones you're likely to encounter when you start using sum types, right? Yes, sum and sum are homonyms. So I keep, if I'm ambiguous, I mean union types when I'm talking about the type itself, and sum when it comes to the sum there, right? So, sorry. I should have been a little bit more precise about these things. Scala actually gives you a clue about how this stuff is actually implemented. So what they do is they have the concept of a trait, which is like an interface, but you can put methods on it, right? And they say, well, we'll create a kind of abstract base class, and then we'll derive two non-further derivable subclasses of that abstract base class, and we'll make that hierarchy fixed so that when someone talks about the abstract base class, there's only that known set of derived classes that implement that abstract base class. So that is to say, there can never be another case class that extends maybe. So maybe is always either a none or in this case a sum. Yeah? Now, so this is actually both good and bad. Turns out that because they use this specific mechanism of doing it, type inference sometimes fails. But the thing to note is that at this point, between the F# 3 lines and the Scala 3 lines, this is really all that functional programmers have to say in order to get a union type. Everything else, that is the value semantics around it, the pattern matching around it, the closed nature of the hierarchy, all of that's encapsulated in just those 3 lines. So all you have to say is the 3 lines, and you get yourself an honest to goodness algebraic value type that you can work with. But of course, C#, you've got to do a little bit more work to make that happen. So what we'll do is we'll start by taking the structure of the Scala thing and flesh it out to what it really means to be closed, so that you can't inherit any further, and also to make sure that we have some value semantics around it. So in terms of the structure, the way, because we don't have traits in C#, you would create an abstract class. You would give it a private constructor so that nobody else can instantiate that class from anywhere. And then because it's abstract and now private, the only place you can put anything that derives from that class is actually inside the class itself. So we'll create 2 classes, make sure that they are sealed so that nobody can inherit from those classes and try and do something else. And this gives you effectively the structure of what it is there. But obviously we're not done, because there's no way to create an instance of the none or the sum now. There's no way to create a value. So you've got to, in addition to the stuff that you had there, create a couple of value constructors. So none, because it does not carry a value with it, simply becomes a singleton. And sum becomes, you have a method called NewSum that gives you back an instance of the sum with a specific value, right? There's a reason why that NewSum is there. I'll come to that in a bit, but just bear with me for the moment. Now, you notice that none already now has value semantics, because the only way to get a none is to call none on maybe, and the only none you're going to get is the same none that you'll get every time. So none is a value now, just by virtue of it being a singleton.
Is it a value by type of A?
It is a value by type. This is an open generic class. So maybe on int will be different. Maybe on int of none will be different from maybe on a string of none, which is as it should be. Which is as it should be. Go on. Did you have a question? Sorry. But the sum is a little bit more troublesome. If I give you a new sum of 5 and another new sum of 5, you will get 2 different objects. Now you want to be able to compare the 2 of them and actually say, hey, these are the same thing. But this will not give you that, so you have to put that in. And in order to do that, we now have to do some more ceremony, right? And this is only part of the ceremony. This is on the outer class. The outer class must declare that it is going to be equatable to itself, and also it believes in structural equality, not reference equality. So you've got those 2 tags that you've got to put up there. And then you've got to write these 5 methods. And strangely enough, the 5 methods reference 2 methods that aren't there in this class, because those 2 methods are actually overridden in the derived class. So if you think about what equals is doing, the strongly typed equals says, hey, make me an object and then compare me as an object. Given an equality comparer, also call equals. But then there is actually no equals of object in this class, because it's an abstract class, that's fine. You expect all the derived classes to implement the methods that aren't there. And indeed they do. So none overrides equals on an object and implements get hash code. And similarly, sum does that. And if you do this mumbo jumbo and stand on 1 foot and wave a dead chicken long enough, you will get value semantics. Okay, now we've done value semantics. Given 2 objects, we know how to compare them for equality sensibly. Go on.
Is the intention to make it a deep value equivalent? So if you've got a sum of a reference type, what are you expecting to happen there?
Yeah, that's a very good question. So the moment you start taking your foot off one boat and putting only one foot on the other boat, you're going to get yourself into all kinds of strife. So in some sense, this approach is a gateway drug to C# users to do proper FP. So you get them to the idea that value semantics is actually a reasonable way to think about objects and their identity and so on and so forth. The strong recommendation is once you get into using value semantics, you should really be using value semantics all the way through. However, if you do land up using string as one of the methods in there, then you will end up having to do the equality to be based on the string. So we'll have to generate specific code to make sure that the strings are compared as values, not as references. Yeah, it's a good question though. Anyway, now that we've done this, we can now create an instance of a value, and we can check to see if they're the same. But you actually can't get the value out of it. If you notice, when we created the property, we made it private. So there's no way to get the value out. So if you have sum of 5, it'll tell you, yes, okay, I can give you a sum of 5. I can give you 2 sums of 5. And even though they're both different references, I will tell you that they are the same thing. But there's no way you can actually use the 5 in any computation. Now you've kind of like locked yourself into this thing where you've created these immutable value types, so there's no way to actually use the value. So in order to do that, you need to find a way to extract the value without polluting it. And so the way we do that is by implementing rudimentary pattern matching. So you create a match function on the top with a lambda for each of the various choices that you have. And if you think about it, that's really what pattern matching is. You give it a function for each of the choices, and the right function will fire. And so on the outer class, you make it abstract. And on the inner class, like good object-oriented programmers, we override and delegate to the right class to do the right thing. So the none class will only exercise the none func, and the sum class will only exercise the sum func. So given an instance of a maybe, when you give the match function 2 lambdas, you don't know which kind of maybe you have. There's no way to actually inspect short of reflection. There's no way to inspect the object to find out, am I a none or am I a sum? But when you give the match function a call, the right thing will fire. So in some sense, you've actually occluded yourself, made it really safe, and removed a great deal of obfuscation from removed a great deal of pain from having to write a switch statement. Because the problem with switch statements, as we all know, is that one is you have to match against the type of the object that you're switching on, which is dangerous. And the other is you will go and add a new option somewhere in there and forget to update your switch statement, at which point you'll get a runtime exception. This way, you can't get a runtime exception because you have to actually provide a handler for each case in the match function, and the compiler will scream loudly if you don't do that. Right? So in some sense, we've come to a safe, possibly cumbersome way of dealing with the thing, but it's definitely value-based, and it's definitely closed, and it's definitely compile time safe, as in the compiler will complain if you change the definition of the abstract base class and remove, say for example, an existing option. You will be forced to go and look at all the places in the code that would have relied on that case. So in sum, it's probably a good thing that it's got to this point, but it's a little different from what we would expect from a traditional bit of code. Anyway, I've been really good to you and kind, and I've sort of given everything to you in bite-sized pieces. So the time to see the full horror of the thing is now, right? So if you think about what that is, how do I get the mouse on this thing? This is actually an enormously long bit of code now. As you can see by the size of the scroll bar, I can't find a way to get the mouse on. I'm sorry. Oh yeah, here we are. Oh. It's actually, oh. No, the mouse is actually a bit funny, sorry. But it is actually a very, very long piece of work to get to the, to see the whole thing. And I think at this point, you might actually have cottoned on the fact that the reason why people don't do some types in C# is because of all of this ceremony, right? And it's just boilerplate code. What you want to be able to do is write 3 lines of code. What you'll end up having to do is to write precisely a whole ton of stuff that is extraordinarily cumbersome and difficult to get correct. And so, what's your choice at this point? So it's boilerplate code, right? So what do we do with boilerplate? We code generate it, right? Now, I felt a great disturbance in the force just now. Like million voices cried in terror and pelted me with XML, right? So basically what it is this, right? We want to write the code, but we would prefer to have the code available to us without us having to write it. And in some sense, we want to write some nice idiomatic C# looking thing so that the F# guys don't make fun of us anymore, right? And we get a chance to make fun of Scala, then that's good too, right? And so what we'll do is we'll come up with a little language for that. It looks sufficiently like C# that you would look at it maybe a little bit longer to say, hang on, that looks a little funny, but it kind of makes sense, right? I mean, what is that? Anyone can read that out. It says union may be of A is either a none or a sum of A. Reads cleanly enough. Actually, terser than F#. And does not telegraph the fact that it actually is built using an abstract base class kind of thing that you would have to do with Scala. So I think we've met all goals at this point. So the trick is to take something like this and put it in your Visual Studio project and have it just work. You want to be able to reference a maybe type in the rest of your C# code, and life should just go on. That's really what we want. So there's, thankfully, a way to do that. And this is where the whole FP side of the mentality of you solving the problem comes in. So we created DSL, a domain-specific language, which is what that was. And then we have a way of processing that in place. So we take the text and parse it into some form of an abstract syntax tree and validate it to make sure that it makes sense, right? And then we reach over to Microsoft and say, hang on, you guys have been working on this Rosalind thing for some time. And for those people who aren't aware of what Rosalind is, it's Microsoft Compiler Services that's now basically available as a library if you want it. So you can do all kinds of your refactorings and all of that. That's all done using like proper compiler support from within the tooling. And you can take an AST and convert it into a Rosalind AST, and Rosalind will happily spit out C# for you. Or VB.NET if you so prefer, right? Although that's left as an exercise to the reader. I'm not going to deal with that just now. So what we've done, so this is the approach that I'm planning to take. And I'm going to start by figuring out what does it mean to build a DSL. So the FP way of doing this is to basically design a language, and the language will define The language will be defined by a grammar, but the grammar will be defined as a type. So we'll be using sum and union types, union and product types, to actually define what the grammar of this language is going to look like now. So the syntax that you saw with the union and the none and the pipe and so on and so forth, we're going to convert that into some form of a type that we can then say, hey, this thing represents that piece of text. And this thing can now be transformed into this Rosalind thing. And this Rosalind thing can be transformed into the boilerplate C# code, which will live in a code behind file and you will never have to see it. But you can then just use that text that you started with to do what you need to do. And so, of course, this is where your question comes in. Where's the line between the types that are defined using this DSL and the types that are done natively? And of course, the goal has to be that you should be able to use natively the types that you need from the underlying system, knowing full well that at some point you're going to have to be responsible for handling the reference inequality semantic stuff yourself, right? So for date, time, and things like that, it's not so straightforward. It's pretty straightforward. For string, or if you have your own classes, then you have to actually be careful about how you model those, right? But then you also have to support recursive types. So we designed the DSL to effectively be capable of doing that. At this point, we now move away from the role of the disgruntled C# practitioner and pull on our FP, F# hats and define a kind of AST that looks like that. I've simplified this somewhat. I'll take you down and show you the real code. But if you think about what that AST represents, that's kind of like an EBNF grammar, but it's live. A union type basically contains a type name, some type parameters, and some union members. The type name is a string. The type parameter is a string. The union member has a name, possibly a type parameter. So your none and your sum of t, those things start to come out here. So union member, you would create two of those for the given union type that we had there. One would be a none, which the member name would be none, and the argument type would be none, because there is no argument on it. The other one would be sum and t. And so you build up this structure, and you validate to make sure that people aren't referencing type arguments that haven't been declared. So it's obviously a mistake to say that you want a maybe of type A, but a sum of type T, which would type check in this situation, but you would have to go back and semantically analyze to make sure that the type argument that you're referring to is something that you know about, right? And so now we have this AST type that we can use as the building block of what the sum type looks like. With you so far? Okay.
You said that's roughly equivalent to a BNF?
It's kind of roughly equivalent to BNF, yes.
I mean, what does the word and
So that's a quirk of F#. It really simply means that that set of types is mutually recursive. That is to say, I can define, so in F#, everything's forward declared only. So you can only use things that you've seen before. But if you want to have a mutually recursive type where you have a type that's dependent on another type, then you need to put them together as a block.
like reading the spec, the useless things up top, and then progressively define things.
Yep, up until,
You care about full type.
right. And then you see full type name, and full type name says, hey, well, union member needs full type name, so I should have put full type name ahead of everything else. But then full type name itself needs full type name. So you have a recursive definition there. So the AND simply says that this set of types is mutually referential. There's nothing more esoteric than that. Right? Any questions? Well, lost everyone so far? No.
Might be worth pointing out what record types are.
Oh, so remember when I told you about algebraic data types? Here's one. The thing that is within the squiggly brace is kind of like a struct. and that's a record, that's a product type, like I've told you before. So just for the purpose of this conversation, think of everything that's inside those squiggly braces as effectively a struct that has those members, and everything that has the pipes are basically the choices between the types that you've seen. So those are the sum types, or the union types. Thank you. So now, of course, it's an interesting problem, right? We came up with this nifty looking grammar on the one side that had some text. We have a machine specifiable version of that in terms of this thing. How do you get the text from there to create an object of one of these for you to use? And that's where the process of parsing comes into play. Now appreciate that this is probably really laboring the point to a lot of people who've done this for a day, for their day job, but it's a fairly difficult concept to get around the first time. You're now writing code that writes code that writes code. And that's going to start getting a bit hairy in a minute. So parsing is effectively something that you're going to write a program that takes a text that's given to you, and you're going to create an object out of that. And then you're going to take that object, and through a whole bunch of machination, you're going to write some code, which is actually the code you're going to finally compile. So it's fairly meta from that point of view. So I wouldn't hold it against you if you get a little confused and you want to ask some questions, right? But anyway, what we do is we take, so parsing is a fairly common problem that function programmers have found some neat ways of dealing with. One neat way of dealing with it is to use something called a parser combinator, where you define a parser as a function that chews up a little bit of the beginning of a string of text, and then gives you back a little value and the rest of the text that it hasn't dealt with. And then you take these functions and you compose them together, and they're not just blind function composition, there's actually a way of composing them together called the monadic style of parsing that allows you to build bigger and bigger parsers out of littler ones. And ultimately the goal is to build one large parser at the end of it all that takes the whole text and gives you a single object. And there are libraries for this kind of thing in each of the languages. So Haskell has parsec, F# has fparsec, and fparsec is a nice little library that allows you to basically, it gives a whole bunch of primitives, and then you can build your own combinators on top of that. And in my case, this is in fact the simplified set of parsing functions that you can build to build an instance of that AST value that I showed you. So for example, word is a well-known parser that reads the next word from a text, from a bit of text. So when you want a member name, you just take the word that's there and make it a member name, and so on and so forth. So you can now figure out how to get an optional case member argument, which is to say an optional type argument, an optional set of members, the type parameters, and then finally the last parser is the one that says, please look for the thing that starts with union, followed by something that will be consumed by union type name, which is this parser over here, and which will return a union type name, and then potentially get any optional type parameters, then pull out all the case members in a block that is braced, and then optionally ignore a trailing semicolon, because we're C# people, and then build a union type out of it. So I'm not going to go into great detail about how fparsec works, and there's plenty of material out there that actually allows you to do this, but the idea is to be able to take text, run it through a fairly small set of functions like this, and get back an instance of the AST that we defined. Go on.
So I have a question.
Mhm.
The one thing when it comes to types is that how do I get the information from the database and pass it to an object to actually use in my computation? So my question right now is that when it comes to union types in C#, does entity framework actually support them when it comes to?
So nothing supports union types as first-class objects. Everybody supports some hobbled, non-value semantic version of union types that's cobbled together as a degenerate record in a database with a discriminated union field or something like that, right? So effectively what ends up happening is if you have, 4 choices, the database will be the union of the columns of all the 4 choices that you have, plus an extra column that tells you which type it is, so that only some of them will be populated and so on. And then there'll be some magic to pull things in and out. But none of that's actually like bona fide union types from that point of view, right? But anyway, this is solving a slightly different problem. So we're not so much concerned about the representation of persistence. We're actually talking about transformation from a block of text to something that's semantically meaningful, and then transforming that functionally to do something else, ultimately back into text, which should be semantically meaningful because a compiler has to actually compile it, right? So I'll show you the actual code. This is mostly representative code that I put up here so that you can see that it's not rocket science. The whole parser for the whole language, including the namespace and all the other .NET garbage that has to be dealt with, is only about 50 lines of code. So it's not much work at all, and you can incrementally build it. So if you think carefully about this, look at the last 6 lines of code and compare it with the AST type that you had there, and you'll realize that there's actually a very clean way of actually seeing how this code would generate that. Okay. Ooh, we're running really late. Okay, so now we've done that, we have to do the Rosalind style generation. So we're going to take our AST and conform to something that Rosalind can consume. And before we get there, let's just take a simple example of what Rosalind's AST looks like. So I'm going to take this class, a simple class with just one constructor and a private property. And I'm going to see what the AST for this, that represents this, the AST that would generate the code for this, what that would look like. And it would look something like that. It's pretty bloody awful. It is actually pretty horrendous. Hang on. And it's not really easy to write this code. So, but what we do is we land up having, because we want to stay in F# and we don't want to write C# and everything inside, infix function calls, we have the ability to write a wrapper function set against the Rosalind libraries. And so I've written one that uses a little bit of F# black magic to allow you to represent that class that you saw as a function that looks like that, which is appropriately parameterized. So the class is a function that I've written which wraps the class declaration builder from Rosalind. But instead of putting all the parameters just as a big tuple as C# would expect it, using partial application and a bit of F# magic, you can actually inline the code so that it actually takes lists and things in ways that allows you to write the code looking fairly reasonable. So it turns out that I could write this code by hand. I don't need to write this code by hand, of course, because I'm going to write code that writes this now in the code generator. So at this point, what I'm going to do is I'm going to switch over to Visual Studio, just because I want you to see. Hang on. I want you to see what this code looks like. So I can take that and put it up over here. And oh, this is not great. Sorry. Right. So can everybody see the screen? Yeah. Excellent. Okay, so as I showed you earlier, this is the full AST. And the AST actually starts with using namespaces and everything because you need to define a class in terms of a namespace. So we actually have separate methods for namespaces, and I have some helper methods for building up using and unions so that when you do references, everything works correctly. And so if you think about the AST that I showed you, which kind of looked like just 15 or 20 lines of a strongly typed piece of stuff, this one's actually the same thing, but with all the helper methods built in that allow you to build the choice class, deconstruct the thing as a choice class, and so on and so forth. And the code generator basically now looks like this. So we say, for example, we want to build the union type itself. We can say that the union type takes the union type method and builds a class out of it. So if you start all the way down at the bottom, you can say, I want a class declaration for the union type, and it needs to have the private constructor, the abstract match function, the access members, and so on. And each of these are functions that I've defined further up the class. And so if we look at the equality operator that we had before, this actually doesn't look like the morass of deeply nested parentheses that you would have had to do in Rosalind. By just using F# to sugar the syntax of calling the thing out nicely, you can talk about things in terms of, hey, there's actually an arrow function in here that says, a left, which is an identity, followed by an Elvis operator equals a right, otherwise false. And if you look at the code that gets generated, this is exactly the code that you want, as it turns out. So by basically building these functions, so if you look at the hash code override, the hash code override is basically an arrow method that returns an integer called hash code without any type arguments, without any actual value arguments, which is public and override, and it is that expression. So you can pretty much actually use this desugaring mechanism to make it easy for you to build the kind of code patterns that you want to generate out. And that's kind of how that is done. And I'm going to show you. And it turns out that once you do that, the code can be generated for you. Rosalind will actually generate out proper text that has the C# class and everything in it. What I'm going to skip on is this P6 thing, which is really black magic. It actually allows you to register using Ole and some other things, a code generator for a given file type. And it'll embed that into Visual Studio so that you can actually do something with it. And I'm going to show you how that actually works by creating a project, a test project. And I'm going to talk about, so let's say that this is actually the thing that I want. Now, let's not worry about these three. We're only concerned about maybe, as before, right? And what I can do is, in this, hang on. So if you go to the Visual Studio Marketplace, you can find the C# Union Types Visual Studio extension. You can download it, and it'll automatically install itself into Visual Studio. And it'll give you the ability for you to, for a CS Union file, put a custom tool name in there. And that custom tool name is the thing that you just downloaded and generated. And so if I now save this, so let me say that I'm going to call this, instead of cool monads, I'm going to call this LambdaConf. So it's going to generate something, and my program, which is using cool monads, is going to break now because cool monads isn't there anymore, but I'm going to call this LambdaConf. And lo and behold, I'm actually able to use the maybe type inside my code. So I can actually say things like maybe of string, and it's type checking. It's found the class. I didn't have to write the boilerplate. The boilerplate's actually hidden inside this code. And everything that you saw that I said you needed to do is actually being done. Yeah, so what I did was I just saved the file, and the Visual Studio integration piece says, this file, when I save it, must require this code generator to run, will generate the code for you and run the code behind and so on. And with a little bit more effort, I could actually put breakpoints in this code on the DSL side, not on the generated side, and stuff would actually still, you can actually do that. So it turns out that you can do that, and this stuff will actually run. Funnily enough, because I've also used the trick of generating partial classes and not full classes, I can actually provide link syntax on a monad now. Because all I need is, I need to handwrite these functions on a type that I didn't define, but which got generated for me. And I'm able to create a link query that actually works on the maybe monad. So it's actually a fairly powerful way of doing it, in the sense that once you take the FP goodness that you know about, and you sort of move it into the space where people don't know about applicative functors and the ability to write parser combinators and so on and so forth, and doing type wrangling and the transformation of objects to actually generate code, you can actually take that kind of high-level abstraction from the F# world and spread the goodness to the C# world so that they can actually get something tractable out of it. Now, I've actually encoded union types with my own custom syntax with all of the semantics that are required. That's kind of the thing. I'm sorry, we started a little late, and now I've run out of time. I thought I'd actually have more time. I've breezed through all the material, but I'll be around if you want further questions asked. All of the stuff's on GitHub, so I'm happy to show you, the code. Go ahead and take a look at it. And the Rosalind wrapper is up in GitHub. The C# algebraic type's up in GitHub, and acknowledge these people who have helped me out: Scott Lashin and George Pollard, Ivan Tolson, John DeGos, and of course Microsoft, who sponsored me to come here and sort of do this work on the side. So with that, thank you. Tweet to me, get me, whatever. Thank you.